Alright, this is problem
Now
9.21.
use linear interpolation to find values at state 4.
It asks us to refer to problem 9.2, or 920, excuse me. It's a colder standard using a specific heat at 300 degrees, or 300 Kelvin. Problem 920 asks us to find the compression ratio, cutoff ratio, thermal efficiency, and the mean effective pressure. The values given, we've got our pressure at state 1, temperature at state 1, and then the highest pressure and highest temperature, which is at state 3, because it is a diesel cycle. Next we want to do a PV diagram. So here we have the PV diagram. With this and looking at our values, it makes it really easy to make a nice little table that we can use to keep track of all our unknowns and what we do know. So we can plug in the fact that state 2 and state 3 have the same pressure. And then when we want to solve for the temperature at state 2, we can use this equation here, which is equation 6.43 from our equation sheets. Plugging in our values, we're going to get 7,200 over 95, 1.4 minus 1 over 1.4 times 300. Oops, I definitely forgot the temperature there. 300 kelvins, giving our final answer for the temperature at state 2 for 1033.1 kelvins. Since question 1, problem part A, wants the compression ratio, we can use the fact that the temperature difference and the pressure difference minus 1. Again, this is straight out of the equation sheets. I'm going to clear this out here to make some more room. That'll give us the compression ratio right here. So we'll plug in what we know. We've got the temperature at state 2, 1033.1, which we just calculated, over the 300 kelvins from state 1. And then we've got our compression ratio over 1.4 minus 1. And you plug all this or solve it all out, you're going to get the compression ratio to equal 22.007. Alright, part B is wanting the cutoff ratio, and to solve for that, we can do the volume at state 3 over the volume at state 2 equals to the temperature at state 3 over the temperature at state 2, plugging in the temperatures we've solved for. We have 2,150 kelvins given over the 1,033.1 degrees Kelvin, which we solved for a minute ago, giving the cutoff ratio to be 2.081. That step was pretty easy. I'm going to clean this up here a little bit, and we'll move on to state 3, which is asking for the thermal efficiency of the cycle. Okay, in solving for the thermal efficiency, we can use a couple different steps here because we are going to need the temperatures, or the temperature ratios at least. So we've got this here, which is an equation out of our equation sheet again, and then we can actually modify it a little bit because we know that the ratio from the volume at 4 and 3 is going to be relative to the other pressure and cutoff ratios, which we already saw, or the compression and cutoff ratios, excuse me, because it is a complete cycle, as we show here in the PV diagram. So when we plug in our values for this, we're going to get the temperature from state 3 over the temperature of state 4, which we do not know yet, multiplied by the compression ratio, 22.007, and the cutoff ratio, but if you notice it's actually inverted here, so got to be careful to keep that straight, and then 1.4 minus 1. When we solve all this out, temperature of state 4 is going to equal out to 836.995 kelvins. table right up here. That way we can clean this up a little bit more again. And then we're going to continue looking for the thermal efficiency. Okay, so the thermal efficiency we have here, it's the work over the heat supplied. And then we can actually substitute in the specific heat for across state 2 and 3 and volume 4 and 1 all over the input stage right over here is going to be and then we can actually simplify this down quite a bit, which makes it a lot more manageable, especially since it wants us to use the specific heats at 300 degrees or 300 Kelvin. So the simplified form here, we have everything we would need to plug it all in and solve out for the thermal efficiency. So if we go ahead and do that here, we're going to have 1 minus ratio of 1.4, 836.995 Kelvin minus 300 Kelvin all over 2150 Kelvin from state 3 and 1033.1238 Kelvin from state 2. And that's just the more complete version than the table. When we solve that out into a calculator or something, we get 0.6565, but do not forget, since it is a thermal efficiency, that's actually going to be a percentage multiplied by 100, and we're going to get our thermal efficiency to be 65.65%. Moving right along, next the one we're going to solve for is the mean effective pressure. Alright, we're solving for the mean effective pressure. We know that it is the work over the change in volume. So we can actually modify this all a little bit. Excuse the copy pasting, it just makes it a little quicker to write it out. And probably quieter for you because the tapping is probably loud. Anyway, when we solve this out, we've got specific heats and temperature ratios, which is all stuff we already have. So we can plug in our values to be 1.005, 2150 minus 1033.1 minus 0.718 times, I'm going to move to the next line here for room, 836.995 minus 300 Kelvin. Solving all this out, we've got the net work to equal out to 736.898 kilojoules per kilogram. Okay, as I'm sure you're aware, there's still a few things we need. So we can solve out here using ideal gas for the volume at state 1. We actually do not have the mass, so if we move this all around a little bit, we can get the volume mass off to one side, and left on the other side, plugging in all the values we do have, we're going to be left with this here. So we can actually plug this now all into the mean effective pressure that we already have.
We know the colder standard analysis thermal efficiency
Top to be the work of 736.898 over the 0.63. And then to make, or for the fact that we're looking at the volume at state 2, we can use the ratio that
we gotta find some properties of each state. So state 1 is
giving this to be on the denominator.
300K.
Sorry, I'm sure this is a little messy for you, but when we solve it all out, we're going to get our final solution to be 851.789 kilonewtons per meter squared,
kilogram.
which is our mean effective pressure.
Volume, fixed state one.
So if you were turning this in as a homework problem, you'd probably want to read it a little prettier. And excuse me, kilonewtons per Kelvin. That's what I'm asked for it in kilopascals,
7,200
which
kilopascals is 1.2
that
megapascals.
already is.
And that
So thank you for watching problem 9.21.